remove that material and rebuild it and replace it so that you have brought it back to a structurally sound condition. But we want a project that's going to exhibit characteristics similar to what we're seeing in this particular photograph. There's no obvious visual distresses that would indicate a lack of structural support. You would come through with your non-destructive testing, a falling weight deflectometer, for example, and verify that the conditions of the material subsurface are adequate and up to snuff. And therefore, we have a pavement that by coming in and doing a milling and overlay process is not going to exhibit premature failure because of something that was underneath it that we didn't realize was there. So we want to do a good evaluation of the proposed project, verify that it is indeed a good candidate for this operation, and move forward with the project. We don't want something, and of course this is an extreme picture, but we don't want something that is going to not provide us with that subsurface structure so that we can meet our expectations, and those expectations need to be realistic. Milling and overlay, much like any other choice in the maintenance and rehab arena, have their limitations, they have their place, and so we want to make sure that we're choosing a project where milling and overlay is going to be a good choice for it. Many of us have seen these deterioration curves in the past. A generic deterioration curve such as this is just simply letting us know that the sooner we attack a pavement to keep it up to snuff, the better and our long-term performance will be, as well as the cost effectiveness of that particular pavement. Another way of looking at it is seen in this diagram here, where at certain stages in the deterioration of that pavement, because we put the pavement out there, it gets exposed to both weather and traffic, and its performance life is going to see a degree of deterioration. Distresses will show up, and we want to attack those distresses. Many deterioration curves are going to show us something similar to this, where it provides us with an idea of what might be the right choice at a given time. We should not look at these sorts of diagrams as a tell-all, meaning that if under the PCI in this case, if it hits 60, we go in and we move across the curve and we see, oh, that says hot in place recycling and a wearing course. Well, it may very well be that that is a good choice for this particular pavement, but we should have more that comes into play in that decision making than simply looking at a diagram. But I want to show this to recognize that what we're talking about is mill and overlays, and a mill and overlay is shown here somewhere around that midpoint, in this case rated about 55 on the PCI condition rating. So what I want to discuss is that when we're talking about a mill and overlay, we have a pavement that still has that good structure. It hasn't deteriorated to the point where the structural condition of the underlying and surface layers are such that it needs to be completely rebuilt or recycled in some other fashion. But it's moved beyond the state where simply coming in with something like a chip seal is going to provide us with an adequate resetting of the condition of that pavement. And so we want to keep that in mind when we're selecting a project. Once we selected that project, now we need to design for it. So let's talk a little bit about the design, and I'm going to key in on a few things when we talk about the design, starting with the mix design. No matter what kind of project it is, whether it is a mill and overlay, a simple overlay, if we happen to be doing something new and putting the pavement on a surface for the first time, or if we are reconstructing that pavement, we are going to have an asphalt mix that needs to be placed upon that. And we want to design a mix that's appropriate for the location, the traffic that is expected. And so CAPA has training classes that do a wonderful job of teaching how to develop a mix design. We at the Institute do, as well as others. And there is a reality that not every mix should be placed in every location. So things such as a stone matrix asphalt, an SMA, is an extremely useful tool in a high traffic, high stress, top tier pavement. Design for a low volume road, for example, is going to be significantly different. And so you want to move through that mix design process with the particular road that you're working on and its expectations in terms of climate and traffic in particular to help produce a mix that's going to be most appropriate for that location. we always want to remember, in my opinion, what are we seeking in a mix design? In a mix design, we're seeking to balance opposing desires. We have, on one hand, desires towards strength and stability, and that is going to help minimize some of our different distresses, such as rutting, shoving, and flushing. On the other hand, we want to have a pavement that's going to exhibit good durability, and that is going to manifest itself, poor durability in terms of cracking, raveling, and permeability. And in order to do that balance between the two, we need to come up with the right proportion of air, rock, and aggregate. The traveling public, they don't really care too terribly much about either of these things. What they really want is something that's smooth and quiet and provides them safe traveling so it has adequate skid resistance. There's a lot of discussion in our industry right now talking about balanced mix design, or others are calling it performance engineered mix design. And I, quite frankly, applaud the effort, but I want to point out that this really isn't a new concept. In the world of asphalt, we've been teaching, those of us who've been teaching mix design should have been teaching to create that balance for the longest time, that we recognize these opposing desires and trying to determine a balanced combination of our materials so that we get good performance on both the strength and stability and as well as the durability without forgetting the desires of our traveling public. So we don't want to attack one half of the equation at the expense of the other half. And as a little bit of an aside, when SuperPave was being developed, its marching orders were specific towards rutting. And therefore, one of the things that came out of SuperPave were mixes that were very robust in terms of rutting. As we've moved into higher levels of recycled materials and some other changes within our mixtures, the incidence of problems with durability has seen an increase, especially over the last decade across our country. And so one of the shortcomings of SuperPave, in my opinion, was that there was a desire within SuperPave for a balance, and I'll show you that in a slide in just a second. But in practice, some of that was forgotten because what we're trying to do in that balanced mix design is balance these three criteria. We got our volumetric criteria, our cracking criteria, and our rutting criteria, and we're trying to get a mix that hits that center target. And what I was talking about with SuperPave, there was this desire. SuperPave originally was going to have levels 1, 2, and 3. And not going into a lot of details, level 1 was just a simple volumetric mix design process, very similar in many ways to what the Marshall and Veeam mixtures of the past had utilized. And levels 2 and 3 were going to incorporate performance measures, looking at rutting and cracking criteria and developing a mix that would meet those criteria. So when we talk about balanced mix design today, many people will, in my opinion, rightly argue that all we're really doing is returning to the fold, if you will, of what SuperPave originally intended. And finally now, after a generation, over 20, 25 years, we're finally moving back into what could be described as SuperPave's levels 2 and 3, but we're calling it balanced mix design. Another thing that I want to point out with, when we talk about the design is making sure that we choose a gradation that matches the thicknesses that we're going to build it to. We want to have a nominal maximum aggregate size, and I'll show you that definition here in just a moment, that allows the contractor to produce a mix that they can effectively get adequate density on. If you design a mix that has rock that is too large on its top size for the lift thickness that's going down, the contractor is going to struggle, and it may become impossible to actually get the density on that because you have to have enough room for that rock to move around and densify. If it is too thin, then you wind up with the roller bridging over. Think about an extreme case. If you were trying to put a 1-inch overlay and you have 3/4 and 1-inch rock in there, at some point, all that roller can do is ride across that rock. And so it's near impossible, if not impossible, to get that density. The aggregate does get locked up more readily, and therefore it creates that difficulty in getting that compaction. And then finally, you can actually break the rock. We can see under vibratory steel rollers in numerous locations where that has actually happened. The roller will actually physically fracture that rock. There's a great National Cooperative Highway Research project that was done in 2004 by Dr. Ray Brown and others from Auburn University's National Center for Asphalt Technology, and they have recommendations in there on minimum thicknesses versus nominal maximum aggregate size for fine and coarse graded mixes as well as SMAs. And I have to emphasize, these are minimums, these are not maximums. In fact, you can compact mixtures with significantly thick layers and get good performance. And your neighbors to the west in Utah are actually putting down a test section this year on a truck ramp for one of their ports of entries, where they are going to be laying in a half-inch, a 12.5 millimeter mix in a single lift, and it's going to be roughly 6 inches in compacted thickness. I mentioned NCAT. They have successfully produced and laid similar mixes at the test track. In their case, it was a half-inch mix once more, and it was compacted thickness of 5 3/4 inches. Dr. Dave Tim actually made a presentation on this at last year's conference in Denver, and so I would refer you to his presentation for more information on their work at NCAT. So just in case you have forgotten what that definition is, nominal maximum aggregate size is one sieve size larger than the first sieve to retain cumulatively more than 10%. Another thing I want to point out when we talk about mixed design is the mixture type. We can see some generic examples on this slide of dense graded SMAs as well as open graded friction courses. So the dense graded in this case is going to be our blue gradation line. In this example, the design air voids is about 4%. Our open graded friction course is going to have significantly higher air in it, and they make great driving surfaces because the water is going to be allowed to permeate through that. We do need to have that open air structure, and they're going to have a high binder content, and they absolutely need to have good tack coat for that bonding. And then finally, our gap graded mixtures that fall into the SMA category are commonly going to be designed at 4%, but increasingly we're seeing some of the designs go down in air voids. And I could say the same thing about our dense graded mixes, where we're seeing mixtures that are designed below the traditional 4%. That mix that I've mentioned for Utah on their experimental location is actually being designed, I believe, to 2.5% air voids. And the other thing that they are doing at that particular location that's unique, and I'll talk a little bit about this technology towards the end of this presentation, and they're using what's known as a high modified asphalt binder. So very rich in polymer binder. So what characteristics do we want for those surface layers? Since we're talking about mill and overlay, we are inherently at the surface. We want to use our highest quality materials, both for the aggregates and the binder. It's not uncommon that we will see lower layers utilize materials that are of lesser quality in particular projects, simply because the demands on them tend to not be as great. But as we get to that surface, the demands on both the aggregate and binder are magnified because of the increases in the stresses and strains that we see at that particular location. We want them to be impermeable, and so we typically design to 4% air voids. And we also commonly will be seeing finer mixes being used towards that surface than what we might see deeper in the pavement. Across the country, the most common mixtures that we see today tend to be 12.5 millimeter and 3/8 half-inch, or a 3/8 9.5 millimeter mixtures. If we would move back in time, say 20 years ago, it would have been increasingly more common to see the 19 millimeter and 3/4 inch mixes at the surface. Those days in most locations tend to be dissipating, if not gone completely already. If we're looking at that open graded course, again, it's going to be about 15% air voids. We do need to make sure we have that heavy tack so that we get that good bond. It's important in that design and construction that we don't create a bathtub, and so we want to make sure that we're daylighted out to the side, so as that water gets to that surface, it migrates through the surface, hits the impermeable layer below it, and because of the crown that will have been built into that layer, it runs out the sides and doesn't pool. We want to make sure that we're careful with future maintenance on these particular projects, so we don't plug them up in the future with a fog seal or with a chip seal or something along those lines, as well as want to be careful when we're building the joints between our subsequent pulls with the paver, so that we're not, again, creating that bathtub effect. when we're looking at these surface layers, I mentioned how we've been going increasingly to smaller maximum or nominal maximum aggregate sizes at our surface. And there's this old misconception that large rock is stronger. We have plenty of examples at the NCAT test track, for example. They have very successfully and even to their own surprise built 4.75 millimeter mixes that far superseded any expectations that they had in terms of performance. We know that the size of the aggregate doesn't inherently build a strong aggregate structure. It is that aggregate skeleton creating that good uniformity, getting good aggregate interlock from top to bottom within that size mixture with non-segregated material that produces that strength. So ultimately, mixture strength is going to be determined by the aggregate shape. We want something that's cubical versus rounded, and we want something that has good texture so it gets that skid resistance for the traveling public. We're going to select the appropriate binder for the location. And again, at the surface, we're typically going to be using a higher quality binder than what we might choose to use deeper in the structure. And we have to have good construction practices, getting uniform placement, again, not segregated, and getting adequate high density to improve that long-term performance. Some of the things I would encourage you to consider are going to be some of the alternate binders that are out there today and that are continuing to be developed. Most of these are still petroleum-based, but we are seeing some non-petroleum-based products that are finding their way, as particularly in the experimental and research phase. And it's foolhardy to think that they will not become a bigger player in the future. But for today, we are still going to, and for quite some time, we will continue to use petroleum-based products. They have served us very well and can be done very environmentally friendly. And one of the products that's getting a lot of attention and is what they're using over in Utah on this experimental section that I've mentioned are what we know as high polymer or highly modified materials. So they have extremely high polymer contents, typically above 6.5% of a block copolymer commonly, which by comparison, most of our polymer modified materials are going to be between 2 and about 4% modifier, depending on the grade of asphalt that we're talking. They have excellent long-term performance that has been seen on installations in various locations, whether it's at the test track or actual field projects. And interesting, I mentioned on this third item, the studded snow tires, that really comes from work that's been done in the Anchorage area up in Alaska. By far and away, their most notable distress for the city of Anchorage is studded snow tire rutting, and the installation of the highly modified material in that location has significantly reduced the incidence of it. They're getting longer-term performance. Of course, it's going to be higher in initial cost. Polymer is a very expensive component relative to the other materials that we tend to see in our asphalt binders, and so your first cost will go up. And in order for that to work out in a life cycle perspective, you should have that return on performance. And so the reduction in both rutting and reflection cracking, as well as in places like Colorado where you have studded snow tires, should help offset that to make it worthwhile. Another technology that we're seeing increasing use of, and this is, again, is not necessarily a new technology, and highly modified materials, by the way, have been tried throughout time in our industry from the late 70s until now. But the process that has been developed and is incorporated today is proving itself to be more friendly to the contractor themselves, and the installation process is not as onerous as what it once was. Fibers, again, are something that have been around for a while. There are different kinds of fibers that have been offered throughout time, and we continue to see those changing as well. The real key if fibers are going to be used in installation is that we get good uniformity, that we get good dispersion across the mixture. We don't want to have pockets of fiber. We want to have that fiber uniformly spread throughout the mixture. Again, higher initial costs, but we have seen excellent performance for both rutting and reflection cracking. I can't say anything about studded snow tires because I haven't seen any research on it, and so I can give these guys 2 bullets that have shown proven performance, but that third one, I'm not saying it won't help with it, but I am saying that there's no evidence that has been shown to me of it. So that's a brief overview on the construction, or the design, excuse me, and some of the things that we want to be most cognizant of when it comes to design. And so I recognize that that's pretty abbreviated, but those are the high points that I really want to emphasize. Again, good project selection, good selection of materials, namely looking at the high quality binders, as well as good quality aggregates that are properly sized for the installation that we're talking about. Now let's move into the milling portion, milling for performance. First of all, let's recognize that there are a significant variety of pieces of equipment that are out there, and most notably various designs of milling heads. In this particular slide, we can see two examples. Both of these are courtesy of Wirtgen. The head on the far right is going to produce a much finer milling surface than what we would expect to see from the one in the center. And there's advantages and disadvantages of these, and I would highly encourage the contractors who are selecting and trying to make those selections to work with the suppliers, whether it be CMI, Wirtgen, it does not matter. There's plenty of great companies out there producing this equipment. They're the experts on the selection of these heads, and they can give you the advantages and the disadvantages. A more open design, such as we see in the center, you should be able to mill much quicker than you could with that finer design. But if you're in an area, for example, where you have significant motorcycle travel, the pattern that is produced and the texture that's produced with a finer design tends to be safer for them, for example. And so there's a variety of different things that come into play. Our MS-22, which is our asphalt construction manual, provides more information on that as well in Chapter 7, as we see in that little box in the lower left corner. So what do we want to be aware of? Well, first of all, we want to select a milling depth that actually removes the distresses. If we've had good project scoping and we've done a nice job of evaluating what's going on subsurface, we should have a pretty good idea how deep that milling should be to begin with. And I say we should have a pretty good idea because there's certainly various instances where we get out there and we think that we need to be at a certain depth, let's just say 2 inches, and we get into the project and we find that indeed at 2 inches, we're not removing everything. Now, that's going to require most likely a change order that would have to run through the project manager and engineer and so forth to determine what is going to happen when that scenario presents itself. But strictly looking at it from a performance perspective, I'm blind to the cost because I have that privilege in this presentation. I'm here to tell you that if you have not gone deep enough to remove that distresses, your absolute best choice, and I would perhaps argue only choice, is to mill deeper. Again, I have the luxury of not having to worry about the cost of such a decision, but I'm looking at it strictly from the pavement's perspective, and that is what's best for the pavement. You do not want to have a scenario such as we see in this photograph where we have these scabs. And this is not that uncommon. If we have a milling operation and the milling depth takes us to a previous interface between construction layers, that milling operation is not always going to produce that beautiful smooth surface that we're hoping for, and we may have these sorts of scabs. And so the question becomes, if you see that, what should you do? Well, again, like I just said, hopefully you see that early. And if you do see it early, it may be an opportunity to pull the milling head up slightly and eliminate those. But if you have this sort of situation, my strong recommendation is to come back and peel a bit more material off with a second run of the milling head. So what kind of advantages do we get? Well, hopefully it effectively removes that deteriorated pavement. I say hopefully because if we haven't quite gotten to the proper depth, we may not have succeeded in that endeavor and not have that result. But we're going to assume that we have reached the proper depth, so we've removed that deteriorated material. The removal of that deteriorated material keeps that distress that was present before from reflecting through in the new material that we're going to place down. Another thing that's very important with milling is it provides an opportunity for improvement of smoothness. When the milling operation is going, they can mill to depth or they can mill for smoothness. And by milling for smoothness, particularly if it's a single lift overlay in that mill and overlay operation, you inherently improve the end result smoothness. Because if you only mill towards depth, and I will point a strong, ugly finger at my home state of Montana, Montana requires the contractors to mill to depth, and then they require the paving contractor to achieve a level of smoothness. They are severely handicapping that paving operation in achieving that goal. When you mill for smoothness, you have one more operation that has been utilized to help improve that smoothness. And so I highly encourage milling to be done in that fashion. Of course, milling provides us with wrap material, our recycled asphalt pavement. We can very effectively reincorporate that material into the new pavement that's going to go down. Long history in our industry of being good recyclers and responsible recyclers, and that effort continues. And so our best source of wrap is almost always going to be from the project that we're working on. And the other thing that milling does is it provides a highly skid-resistant surface. And a bullet that I should have added is also helps improve that layer interlock between the older layers and that new material that goes down. When we have that milled surface, whether it be a fine mill or a more coarse mill, you do improve that layer interlock and bonding between those with and without tack. Now, you're going to hear me say you should still tack it, but milling doesn't always require it. But tack is such a cheap insurance policy that I encourage it nonetheless. So the surface texture, I've mentioned that we have different kinds of heads, fine and coarse. That's going to be directly influencing the type of texture that we have. Both the carbide bit spacing and their condition, these bits do wear out. They should be checked at least daily, and those that are severely worn or worn to the state of predetermined deterioration get removed and replaced on that milling head. The depth that we cut to helps have a influence on the surface that's produced, the speed of the rotation of the head, as well as the speed of travel. These two in particular should be balanced to produce a nice, beautiful pattern. I say that we should mill towards grade, not towards depth. How do we control that? Much like we do on our paving operations or some of our other equipment with a ski, string line laser are all options. GPS is increasingly being used as well. We want to measure that profile commonly, and that can be done with a profilograph or some other profiler, but it's not uncommon on projects where that it does not happen. So that's not a big deal. What we're looking for, what we're seeking is a surface that looks something along these lines. This is a beautifully milled surface. This particular photograph came from one of our suppliers of milling heads. And so they, of course, picked one that they were very happy with, which I must say they did a great job with. And as we have here in this verbiage, note that chevron pattern. That's what we're seeking. There's a nice match that occurred in this operation between that rotational speed of that milling head as well as the forward movement of the milling machine. So profile milling is what we're seeking. We recognize that the depth will vary when we do that. Much like when you're doing a pull with a paver, if you are trying to improve that smoothness, you are trying to improve from what was down there below. And since that surface was not perfectly smooth, we didn't have perfect longitudinal smoothness previously, we are going to inherently have to put more material down or remove more material in the case of a milling operation in some locations than others. Again, we're going to use the typical types of grade control, and then we may be looking at measuring that afterwards. Regardless of whether it was done for depth or for smoothness, we do need to make sure we clean that, and that can be one of the negatives of the milling operation, particularly if you're working in a nighttime scenario where you have a very finite, clearly defined window of operation, and you have to come in, set up your traffic control, do the milling operation, clean that milling operation, tack that surface, and then do the paving before the particular roadway needs to be reopened to traffic. That cleaning operation can really eat up quite a bit of your time. If you are not under that scenario where you can do the milling, you can clean it, but then you can leave it open to traffic, particularly traffic that's traveling at higher speed. That traffic does a great job of helping to clean out those microfines that a brooming operation in particular, and even to some extent a vacuuming operation, may not quite get all of that material out, especially again if it's in that closed time frame scenario of nighttime paving, because in the milling operation you are going to incorporate moisture to help keep your teeth cool and assist in that milling operation. That of course will cling to that dust and create more of a paste, which is difficult to clean up. But we want to do our level best to clean it as much as possible. And so our goals are going to be that it would be free of debris, minimal or no dust, and we want as dry a surface as we can come up with. We are now ready to tack that surface. So let's talk a little bit about the importance of tack. So as I said at the beginning, I'm a soapbox tack guy. I am a huge believer in tack coats. I was in charge of, with Jason Dietz with the Federal Highway Administration and delivering tack coat workshops across the country. We did that in nearly every single state. We didn't actually give the workshop in Colorado, but we made numerous presentations at this conference. And the end result is that the use and importance of tack coat is receiving increasing attention across the country. So what do we want to do with tack coat? Well, we want to make sure, first of all, that we have a good application of it. The picture in the upper left is from just east of Colorado Springs. And this particular contractor did a great job of applying the tack coat slightly wider than what the pole of this lift is. That's excellent. What we don't want to have happen is what a really good friend of mine who's a contractor here in Montana did on this particular project. And the project that we're looking at happens to be an NCHRP project that NCAT was doing the research on. It was a warm mix topic. But what's interesting is my friend Mike, who has been running this operation for years, they did a beautiful milling operation, as we can see in this photograph. They did a decent job of applying the tack coat, but notice that their tack coat isn't quite wide enough. The most important place for tack is going to be the wheel paths and that longitudinal joint. And in this example, the lack of width in that tack coat is setting up for a potential compromise in the performance of that longitudinal joint. And what's really interesting about this particular project, and I was one of the many who was out there, I was out there, the state materials engineer was out there, the state materials testing engineer was out there, the state pavement engineer was out there, as well as about a half a dozen folks from NCAT. We're all out there, and we watched this operation happen just like this, and none of us recognized what was happening in terms of the width of that tack coat until I was examining these pictures, and it dawned on me that we were all multiple experts, quote unquote, but we were all idiots, and we failed to see what should have been seen by someone with much more limited experience than all of us. So my point on that is that we do tend to get complacent in some of our operations. And so again, let's pay attention to those details. In this case, the details of how to apply tack coat, making sure that it's wide enough, slightly wider, like we've seen this great operation for a Colorado contractor on the upper left. What we don't want to have happen is like we see here. And unfortunately, once again, this is a photograph from Colorado. I took this particular picture. And the thing that I want to point out is look at how inconsistent this tack coat is. Not only are we looking at inconsistency longitudinally down the road, but also transversely across the road. And so there's clearly something going on with this tack distributor that needs to be addressed, a maintenance need, if you will. When we start looking at tack coat, we don't have to reduce the bond of these layers significantly to have a huge effect on the performance of that pavement. And so in this particular example, I would expect that the performance of this layer is going to be hindered negatively because of the tack coat application. Again, we want something that looks much more rich and consistent, like we see here. Very consistent. There's a little bit of scraping that's happening with that cold cal pickup as it's moving along, but overall a very nice operation. This is Boeing Field in the state of Washington, so an airfield, and beautiful tack coat operation here. So why do we use it? Well, to begin with, it promotes that bonding between the layers. It's absolutely vital for that structural performance. that photograph I showed you from Colorado, where I was just a few seconds ago discussing the lack of performance that happens with a slight reduction in bond. There's different numbers that we see from researchers, but somewhere around a 70% loss in expected pavement service life from only about a 30% reduction in the bonding performance. This happens to be for some research in Texas. And there's, like I say, various other researchers that have come up with similar things. We do not want to have that slippage between those layers. Tack coat also provides additional moisture barrier. It helps to provide that good performance of our joints. And so we want to make sure that we get a good tack coat at our longitudinal joint. But we also want to make sure that we get good bonding between our transverse and longitudinal vertical surfaces as well. And so we want to, if anything, I like to say, let's overdo the tack. What happens if we don't get bonding? Well, this happens to be from some research that happened at the test track down in Auburn, Alabama. I'm not going to spend a huge amount of time on this slide, but I just want to point out that the, I'm trying to find, unfortunately, I'm not finding my laser. And so, here we go. If we look at this top design, let me step back for a second, I'm sorry. In this particular setup, what they were trying to do is look at the benefit of what's known as a rich bottom layer. And at NCAT, they are so, they being Dr. Buzz Powell, a real good friend of mine, who's given many great presentations in Colorado in the past. He is the consummate field researcher, and to the point where when it comes to tack coat, they actually calibrate their distributor truck for every single application. And so when they come up with a design for a particular shot rate on an experimental section, they calibrate that truck and they have extremely high confidence that they hit that number very well because of that calibration process. So they're trying to display and show the benefit of a rich bottom layer. What they had for both of these two sections is a bottom layer, in this case on the top, that was designed traditionally. They increased the asphalt content down here at the bottom by 0.5%. This middle layer in both locations was identical. It was a high recycled middle layer, 40% wrap, and then the top layer in both locations was an SMA. All the binders were identical. All the aggregates were identical. The gradations were identical. The only difference between these two was that extra 0.5% asphalt in the bottom. They applied their tack coat. It was a non-tracking product. They applied it at the prescribed application rate of 0.5 gallons per square yard, and then they started running their trucks on it. The anticipation was that this bottom layer, the bottom design, excuse me, was going to have superior performance because of that rich bottom layer, eliminating tensile cracks at the bottom for that bottom up resistance to bottom up cracking. What actually happened was the performance turned out to be pretty lousy, and that is because of the debonding that occurred between these two layers. If we come over here to the stress strain diagram, looking at the top, if we have good bonding from top to bottom, we will see this beautiful distribution of stress from at the top of peak compression to the bottom of peak tension. One place I want to definitely point out is the horizontal microstrains that we see between that recycled layer and that bottom layer. Notice that with proper bonding, the microstrains at this location are less than 50, somewhere around 35 to 40 microstrains. But because of that debonding, now we have a disruption of that distribution. And in fact, the amount of horizontal strain at the interface, which is now acting effectively like the bottom of the pavement, is significantly higher than that 35 to 40 microstrains. In fact, it's somewhere north of 150 microstrains, around 170 microstrains. Where that really becomes a significant issue is when we remember that this is a heavily recycled layer. It was designed to not be resistant to tensile strains. And so bottom-up cracking was initiated in this pavement and in this location not at the very bottom of the asphalt layers, but at the bottom of the bonded asphalt layers that SMA at the top bonded to the recycled layer. And so cracking occurred in this location between that rich bottom layer and the recycled layer and propagated up to the point where they had to divert their trucks around this section and halt operation, rebuild it, and continue on. And the thing that I also want to point out, excuse me, is that all of these sections had extremely good density. They were consistently built between 93 and 94% density. And so one of the things I like to point out is that even if you get good density, if you don't have good bonding, you're not going to get good performance. Okay. I'm sorry. There we go. Turn my annotations off, and now I can move forward. Oh. So, summary of tack coat. Plays a significant control in the compaction process. That picture that we saw in Colorado where it was, the tack was applied slightly wider than the ribbon that was being compacted, that tack coat helps provide some confinement. And so that roller running along that edge does not tend to shove that material out as readily as it might without that tack coat. It does create that bond. That's what it's there for. It's the glue between the layers. A poorly bonded pavement will experience fatigue much more quickly. The example from NCAT certainly bears that out. We want to make sure that we apply it consistently and at a good width, and it is vital for this performance, but it's a very low-cost insurance policy. So let's talk about our final topic today, density goals. We have, again, recognized the need for compaction pretty much since we started building asphalt pavement. So for well over 100 years, we've been researching and attempting to improve and come up with new means to improve that density. And especially in today's modern era, post-super pave, with the high quality aggregate requirements and the high performance binders that we have today, some of the concerns that historically were present in getting too much density have, either waned or completely gone away. But even before those materials were available to us, the need for compaction was recognized, and two of our deans of asphalt, if you will, today, Dr. Chuck Hughes and Dr. Ray Brown, in independent research, both are essentially saying that the most important thing that we need to do when we're building our pavements is get that density. Nothing affects performance negatively quicker than a more open, dense graded mixture than what we had intended for. And in fact, there's plenty of research, and I'll show you one example of it from NCAT here in just a moment, that shows that there's about a 1% decrease in performance, about a 10% decrease in performance for every 1% decrease in compaction. So why do we compact? First of all, we want to minimize further consolidation. I like to say when I'm talking in construction that your pavements will all get their density. Your density is either going to be achieved while you're constructing it under the rollers, or it will be achieved in what I like to refer to as rolling pneumatic rollers. We call them semis. Either way, your pavement will get densified. It's just a question of when and by whom. And the real problem with those semis isn't that they densify our pavement, but they're not kind enough to move back and forth across that pavement, and so they tend to channelize, and we call that rutting. So we get that good compaction that helps provide good shear strength and resist that rutting. We see improvements in fatigue cracking, certainly with good compaction. For some people, it's also surprising that we see resistance to thermal cracking improved with good densification. We want to have impermeable pavements, and densification is how we achieve that. This helps to minimize that oxidation of the binder, and ultimately it gives the traveling public what they're looking for, that smooth, quiet ride. All of those are elements of durability. The NCHRP report that we referenced previously on lift thickness to nominal maximum aggregate size also has this statement: when it comes to the level of compaction that we're seeking to achieve, they found that regardless of the gradation type, that somewhere around 6 to 7% air voids, so we're talking about 93 to 94% density, we create impermeability in our pavements. Another thing that's important to recognize is that compaction helps to make up for poor materials. Again, various research efforts bear this out, but one of the ones I really like to point to that I've been pointing to in my entire career is what happened at WestTrac. And one of the things that was really notable at WestTrac is that they found when they used poorer materials and lesser designs, but they had great density at the time of construction, that they saw reasonably adequate performance. On the flip side, when they used better materials with better designs, but they had a more open construction result, i.e. they didn't get as much density, then their performance was poor. And so without density, even with good materials, you're not going to get good performance. But with poor materials that do get good density, now you have a chance for good performance. And so again, density is very, very important. I just mentioned this report from NCAD. It came out in 2016. One of the authors is a name that I would think you would recognize in the state of Colorado, Tim Aschenbrenner, your former state materials engineer who's now with the Federal Highway Administration. And again, the summary statement is that with a 1% decrease in air voids, they see an improvement in the extension of service life by about 10%. So you go from 93% density to 94% density, you're going to get about 10% longer life out of that pavement conservatively based on the research, both from field work done within pavement management systems as well as research done at a university type level. What do we do to help control compaction? Well, first and foremost, the number one thing that we have control over is temperature. And it's vitally important that we control that temperature. Dependent upon the binder that we're using, the temperature ranges are going to shift slightly higher and lower. And so we want to make sure that we are operating in a temperature band that's most appropriate for the binder that we're using. We don't want it too hot. We don't want it too cold. Optimum temperature is going to vary with many factors, but somewhere around 300 or so degrees down to about 280 degrees is where we should be starting compaction. And stopping compaction is generally going to be around 180 or so degrees. In reviewing your most recent specifications, you have differing numbers dependent on whether you're looking at a neat binder, one that is not modified, versus a modified binder. And you have specification temperature requirements that vary depending on whether you're using a modified binder or an unmodified binder. So I would reference you to that specification to come up with and see what the appropriate numbers are in the state of Colorado. So when we're looking at compaction, we recognize that there's a number of factors that come into play. From an environmental perspective, both the air temperature and the surface temperature come into play. Both of these are going to affect the cooling rate of the mixture, as will the wind thickness, wind speed, excuse me, the lift thickness. Thicker lifts retain heat longer. There's more mass there. The temperature at which it arrives is going to have an effect. And then whether or not we have clouds out or not, we can see a difference in how fast our pavements are cooling while we're constructing them. There's a couple of extremely good tools that are free, excuse me, that we can use to help estimate the amount of time. You may have heard of them before, you may not have. One is called PaveCool. It was the first generation of these two pieces of software. The second is called MultiCool. With both of them, you have the opportunity to utilize apps within the Google environment. Unfortunately, with the Apple environment, only PaveCool works. But I can tell you that the significant difference between the two is with PaveCool, you can do the analysis for a single lift at a time. With MultiCool, it can do multiple lifts at one time. And I don't see personally in my use of the two of them that is a significant advantage. And so, quite frankly, I wind up using PaveCool almost exclusively because that's what I can use on my phone. An example of what comes out of PaveCool, this happens to be the PC version. We have a number of key inputs that we put into it, our air and our surface temperature, the temperature of the mix when it was delivered. We'll come up with an estimate or a measurement of the wind speed, the lift thickness. We also wind up putting in where we're at in terms of our location upon the earth. We can put in some other conditions in terms of cloudiness and so forth. And once we put and the binder grade that we're using, once we put all of that material in, it's going to generate a cooling curve like we see here, and that's going to give us our estimation of how much time we have for compaction. Where this really comes into play is when we start looking at our tighter conditions, in particular what I'm talking about there when I say tighter conditions, I'm saying that our conditions are not as favorable. You know, in August, for example, we tend to have our hottest days, our longest days, and so the window for compaction tends to be the broadest because our mix stays hot longer in the construction process. But when we move into, let's say, October, where our nights are getting notably cooler and may actually be dropping below freezing, and the daylight hours are significantly shrunk, we recognize that in general, we're looking at less favorable paving conditions. And so when we're in those less favorable paving conditions, if we have the opportunity to increase our thickness just a little bit, we can have a huge benefit to the window of opportunity for densification. In this simple little example, and I did this example based on a project at was right outside of my office in Billings, and this was a later in the year, or excuse me, an early paving operation in March. We had warm days for March, and so they were able to get out there, and the contractor that had called me and asked me, what can I do to try to improve my opportunity to get density? And so I just ran this little analysis, and I showed them that in their case, they were delivering unmodified mix. It was a 6422. They're delivering it at about 300 degrees. And I showed them that if you could just do another ½ inch, they could notably improve their densification window from 28 minutes up to 40 minutes. Now, that for some of you, maybe going, well, gosh, 28 minutes, you should be able to get density within 28 minutes, and I agree you should. But we all recognize that things happen, and just that little bit of an increase, going from 28 to 39 minutes, can be the difference between a smooth running successful project versus one that could be a major headache. So in their case, they went to the city of Billings and proposed that extra ½ inch. They didn't have curb release and so forth that they needed to worry about in this particular project, so it was approved, and it worked out quite well for everybody. Temperature limitations within the state of Colorado, this is out of your table 401-3. You have differing limitations based on the thickness, and that is wise. If you're dealing with your thinner layers, you have to be warmer outside, whereas when you go to your thicker layers, you can be slightly compromised in temperature. Also, depending on whether you're on a top layer versus lower layers, you have different temperature requirements, more stringent for those top layers, which are arguably more critical. The rolling operation itself is pretty straightforward. We're not going to spend a whole lot of time on that. But just for those of you who may not be as familiar with it, I wanted to make sure that we included that. Typically, there's going to be 3 stages to the densification process with a breakdown, intermediate, and finish roller. There's nothing magical about this. There's nothing that says you can't have a breakdown and then a finish roller, and there's nothing that says that you can't have more. I shouldn't say nothing, because some specifications do say you shall have all 3. But in terms of what the pavement sees, all that we really care about is that it actually achieves that density. Mr. Jim Shirachman, who is a respected expert within our industry, has made numerous presentations in Colorado previously as well. He's been very open in his discussion, and he says, quite frankly, I would love to see my projects with a pneumatic breakdown roller and then a finish roller, and I'll get good density all the time. And so I bring that up simply to point out that our goal is density in this portion of the presentation. How we achieve that is usually with 3 steps: breakdown, intermediate, and finish. When we look at what are they actually achieving, the initial densification is going to happen at the paver itself in that screed. Almost every screed that is sold is going to be vibratory in nature. You do need to turn that on. That helps with that densification process. I've operated a screed. I recognize that when you have that vibration going, it tends to, after a while, certainly get annoying, and it can be downright uncomfortable for some folks. Our screed manufacturers are increasingly recognizing that and designing and dampening systems to help minimize that negative effect for the operator themselves. That breakdown roller is where we get the vast majority of our densification. Our best opportunity is when the mix is hottest, and that happens during the breakdown phase. Intermediate is usually going to be close behind that breakdown phase, and that's where we achieve our final density in general. Yes, we do tend to pick up a little bit of density with that finish roller, but very few construction operations are relying on that finish roller to achieve their ultimate density. It should happen at the intermediate stage. The finish roller is simply to make this thing beautiful. It's ironing out any of the defects that may have been caused by the previous rollers in this operation. And that is one of the criticisms that Mr. Schrockman's desire for a pneumatic breakdown roller and only a steel finish is that it's very difficult to completely iron out what a pneumatic roller produces. And so there is that criticism of Jim's desire. A couple of things that we want to point out in that rolling operation as well is that, particularly that vibratory roller, most of them will automatically stop that vibration as we fall below a certain travel speed. And when they fall below that travel speed, the vibrations quit. That is very important when we come to a complete stop. If you have a roller that does not automatically stop and the operator forgets to hit the button that stops that vibration, that roller will settle as it sits. When I was on a roller one time, I'm guilty of that. You cannot roll those defects out. The other thing you want to make sure that you do is you turn into your stop. We can see in this particular example, right up in here, every single time that roller has been coming to a stop, they have been turning into it, creating that offset that allows the subsequent passes of that roller to iron out the slight defect that occurs when the roller stops, whether it's vibrating or not. We want to make sure that the target temperatures are met and that we reach that final density requirement with the rolling operations. So the goals of the paving is going to be continuous. We want that hot plant running continuously throughout the day. And we want the paver running continuously as well. And we want that roller operation to be following the paver at a consistent pace as well. What are we looking for when it comes to density? Well, at the Asphalt Institute, these are our recommendations. We want to shoot for 94% theoretical maximum density. There's plenty of examples where we see this achieved on highways and airports throughout the country. We are huge believers in the percent within limits specification system. We believe that lower specification limit should be 92%, and we do not advocate an upper specification density. So we consider a one-sided PWL. We want to ensure that the density is achieved, and cores are absolutely the best way to do that. The nuclear density gauges and the non-nuclear gauges are fantastic quality control tools, but cores give us that ultimate number. As an aside, those non-destructive density gauges do need to be calibrated to the cores. And we are a huge believer in incentivizing the contractors. And so we believe a 5% bonus for the top level of density is money well spent by the DOT to give that contractor a healthy carrot for them to pursue to get that good density. When we have interviewed experts from around the country and we've asked them about bonuses, the time and time again, the number that they said contractors are guaranteed, and that would be in quotes because there are no guarantees in how a contractor will behave. But when you go to a 5% bonus, that gets their eyes open and they're willing to pursue it. If you're only a 3% bonus, we've heard differing reports on how successful the pursuit of that bonus has been. If you're less than 3%, what we have seen and what has been reported to us is that the pursuit of those smaller bonuses is almost non-existent by comparison. So 5% is our recommendation. We want to talk very briefly about that longitudinal joint when we're doing a mill and overlay operation. If we have the opportunity to simply mill one lane at a time and create good confinement on both sides, that would be ideal. But regardless, we want to make sure that we have good overlap, somewhere around 1 to 1.5 inches, half inch to inch and a half, right about that 1 inch mark, creates a good layer of material to provide material there for that densification. We do not want our loop operators, and notice I refer to as the guy with the loop as a loop operator. They're not a raker, they're not a laborer, they're a loop operator. We do not want them raking that material back as had been the historical practice. This operation will provide an aesthetically a pretty joint, but inherently as we move that material away, we are starving that joint and not allowing for the right amount of material to be there to get that good density. This picture outside of Bailey, Colorado shows what we actually want a loop operator doing. We want them there for when they're needed because things do happen in the paving operation. But notice that this particular longitudinal joint hasn't been raked at all. They've maintained good overlap, this contractor has, and they are getting good density at that joint as a result. They're giving themselves the best opportunity for that density. So when we're talking about greater durability, whether it's going to be a mill and fill operation or if it's going to be any other type of asphalt paving operation, getting that greater durability is really a matter of getting better density in the first place. That inherently is going to increase that first cost. So that's negative to the calculation of a life cycle cost analysis process. But everything else should be benefited from it. We should have reduced maintenance because higher density provides greater resistance to fatigue and rutting. And so that should reduce the number of maintenance operations that would be needed to address those types of distresses. We should be able to extend the life and therefore also extend the rehabilitation cycle. And so that's also hugely beneficial to an LCA analysis. And so with that, Becky, I'm at the end of my presentation, and I have not had the opportunity to look at the chat, so I'm going to pull that up, but I am ready to address any other questions that we might have going on.
Okay. We did have some questions come in during your presentation, and I'll just go ahead and relay to you so that you don't have to ask the question and answer it as well. So, okay. Will the different depth in milling ultimately be a problem with adhesion and air voids being erratic, also erratic compaction obtained? And that's from Tom Clayton, so.
Yeah, okay. Hey, Tom, that's a great question. It shows some tremendous insight, and I have to apologize. You asking this question reminds me that I completely ignored your voicemail to me, so we'll talk about that as well in a minute after this. But will the difference in depth have an effect? Well, if there's a great enough difference, that absolutely can have an effect, and a negative effect at that. Because let's just use some extreme numbers. Let's just say that the milling operation resulted in where in some places you need to put down 3 inches of new material, in other places only 2 inches. Well, the reality is that if you have that much of an extreme difference between your upper and lower bounds, you're probably going to have a notable difference in the air void. In terms of the adhesion, I'm not positive that that would have an effect. I need to think more about that. I think that as long as you have a good tack coat and you did your proper cleaning to start with, you have a good tack coat, you still should have a good bond, but I would be more concerned about the second potential negative, and that your air voids, because that difference in thickness is likely to affect the amount of densification that happens in that rolling operation. And so you could have discrepancies in terms of air void consistency because of those different thicknesses. So great question, Tom.
Okay. And is PaveCool applicable with warm mixes?
Absolutely. You'll have a shift in your input temperature because of delivery, but it will just account for that shift in temperature and give you a corresponding shift to the cooling curve that should reflect that.
Okay. And then can you expand on the topic of strategy selection and deciding if mill/overlay is the right strategy and or how deep to mill? Also, do you recommend milling when there's only 3 to 5 inches of asphalt pavement?
Okay, let me start with the second question first, because that one's definitely the easier one to answer. If you have 5 inches, that's a maybe. If you have 3 inches, you probably don't have enough thickness. And this question is from Tom Peterson. And what Tom is recognizing is that the milling equipment is very heavy and it needs adequate support. And so if you have a thinner a pavement that you're working on, there is a very strong likelihood that it may be too thin to have good adequate thickness. You may wind up needing to think about something like a cold in place recycling, or if the distresses are high enough, it may be time to consider a full depth reclamation where you can still use that material in place and still get the benefit, economic and environmental benefit of recycling it, but it may indeed be too thin to support a mill and fill operation like we're talking about here. Generally 5 inches and greater is probably going to offer you adequate thickness, because you should usually assuming you have good base support, which we said in the project scoping is what we're seeking in the first place. If you have 2 inches or so of remaining asphalt material, it's probably going to support your milling equipment just fine. If you're less than 2 inches, probably not. There's more of a risk of it not. Getting to the first part and talking about the strategy and selection, it really goes back to that pavement management process and project scoping. And a lot of past experience certainly comes into play with these sorts of decisions. And these are engineering judgment decisions. There's not, some people will like to say that you have these hard and fast rules that if in your evaluation curve you're at this particular location, you should be looking at this and only this. I am not that guy, and I will not say that there's one size fits all. So a significant amount of judgment is going to come into play. When we're talking about a mill and fill operation, I am not looking at a pavement that has widespread significant distress. I'm looking at a pavement that is still exhibiting good structural behavior like we said before. It's probably going to have some cracking, but it should not be structural cracking, alligator type cracking. It's going to be thermal cracking. It may be some longitudinal cracking, most hopefully not in the wheel paths. If it is in the wheel paths, that might be indicating that we're getting too far down on the curve. But again, there's going to be a judgment that's related to that. If the longitudinal cracking is reflective of a construction joint, I'm going to be less concerned about that being a hindrance to the future performance of the pavement that we're working on. And so, again, we want a pavement that has fallen down the deterioration curve to a place where something like a microsurface or an ultra-thin overlay or a chip seal is not going to provide the benefit that's necessary long-term. And so we move towards a structural fix like an overlay or a mill and overlay, but it hasn't fallen so far down the curve to where doing that mill and overlay process isn't going to give us adequate return to service and long-term benefit. So judgment is, again, going to be a big part in that decision-making process.
Okay. And then Mike Hayes noted that they do much smaller mills for pothole repairs and cracks. Would a heavier roller be better for compaction, or would a smaller roller with oscillation be better? Also, they do much smaller amounts of asphalt. Would it be better to lay it around 300 degrees, or can they get lower on the temp?
Well, bringing up oscillating rollers, thank you for doing that. Oscillating rollers, for those of you that aren't familiar, is a technology that was brought into our country by one of the roller manufacturers, HOM, and they received a lot of criticism from their competitors, quite frankly, which is interesting because now almost all of their competitors have a similar type product. Oscillating rollers have a different technology and how that they are creating that densification process. I actually have a video for both vibratory and oscillating rollers that shows that, which I didn't incorporate. I can share that with people if they request that from me. I'd be happy to do so. Oscillating rollers are fantastic in urban environments, particularly in some of our smaller communities where we may have utilities that are not that deep underneath the surface where a vibratory roller might create damage. Also on bridge decks, that's another place that they get widespread usage. But they also get a lot of usage in regular paving operations increasingly. And so it sounds to me that in your particular location, you have switched over to that oscillatory because you are getting the densification that you're seeking. And that really is the key. I'm not going to be the guy who sits here and tells you that, oh, this roller is the one you should always use. To quote Mr. Schrockman, Jim says, I don't care if you hop on your pavement in a pogo stick. If you get density, I'm happy with it. Now, I think that might be a little silly to watch, and you might get a lot of TikTok views if you try to do it that way. But the reality is large or small with the roller, if you're getting density, I'm happy with it. The smaller rollers, especially in a patching operation, tend to have some huge advantages in terms of their mobility. And so smaller patches like what you're talking about, I can honestly say that when I've done them, I've never used a large roller just because the smaller rollers in particular, what I've had good success with is a smaller roller that has steel on one wheel and a pneumatic on the other set. We've got a good balance between those two. At the times when I was doing it, oscillatories were not available, but I would definitely give that a lot of hard look if I were doing that today. Your question about temperature, would it be better to try to lay around 300 to get it, or get at a lower temperature? That really depends on the binder that you're using as to where you would want to fall on the temperature curve and whether or not you're using a warm mix technology as well, in particular some of the chemical warm mix technologies. Again, the bottom line when it comes to temperature is getting that density. You don't want to get too hot because then you damage the binder itself. And so I'm assuming that we're at a temperature range where we're not damaging this binder in the first place. And so get your mix there at a temperature that allows you to get that density using the rollers that provide that as well.
And then do want to just note for those that are still on the line that Jeff Weitzel did make a comment too that WMA additives improves the window and ability for densification. So appreciate everybody staying on the line. I know that we went over, but the beauty of virtual meetings is that we can post the entire recording. So those that had to jump off early will be able to get the full Q&A. And Dave, thank you so much for the presentation. Very informative. Do want to also let folks know that to join us next Thursday on the 4th at noon, we will be presenting on using ground penetrating radar for roadway applications with Joe Ryder with ARA. And the presentations for everything it will be every Thursday through March. And the topics are on our website. We'll be posting the handouts as well as the links for the recordings. And also remember to join us April 30th at Bandimere or May 5th at Mesa County Fairgrounds for the Asphalt Appreciation Day and Expo, where we'll have equipment, vendors, and some food trucks. So again, Dave, thank you so much. We really appreciate it.
It's been my pleasure.
Good job, Dave.
Thank you, Tom. And thank you, Tom. Always appreciate the opportunity to do work with you all in Colorado. I just so look forward to our actual face-to-face gatherings once more. These virtual are very useful in many ways, but they just, in my opinion, can't replace the interpersonal reactions that we get. And so I look forward to shaking people's hands and enjoying adult beverages and fine dinner together once more.
Yes.
Dave, would you mind if you just shared your email address if any follow-up questions for you?
Oh, absolutely. Let me type it into the chat, and that way there it'll be permanently remembered. And let me make sure I spell it right.
The Asphalt Institute is a great partner to the asphalt industry. They support us here in Colorado. Dave is the Rocky Mountain Region Engineer, available to help throughout the Rocky Mountain West. Excellent resource on asphalt binders, tack coats, compaction, airport paving, and both to the user as well as on the producer side. So I'd encourage anybody and everyone to jot down Dave's number and email and get a hold of him if and when you need him. So thanks again, Dave.
Well, and I thank you, Tom, and I'll just throw one more thing out there. My desire to get out of my office is so great that anytime you contractors need somebody to get on the field, by all means, call the folks at Kappa. But go ahead and give me a call, too. If I have an excuse to get away, I will be happy to do so.
That's great. Well, thank you, everybody. Please stay safe, and we will see you next Thursday.